Thank you to be here today. This is our third webinar organized from the CBS, which is the Commission of Volcanogenic Sediments of the EFSA. In this occasion, we have a presentation from Lucia Dominguez. She is a postdoctoral researcher from the University of Geneva, and she nowadays is working on the remobilization of volcanic ash in the group of Costanza Bonadonna. So thank you, Lucia, to join this webinar, sorry. And you can start if you want. You're ready.
Okay. Well, thank you very much, Manuel, and all the commission to having invited me. It's a pleasure to be here in this volcanogenics community. I will present a work that I have done during these last 10 years, I will say, with many institutions, many collaborators, it's a multidisciplinary research with atmospheric and erosion and volcanology science. So it's really a combination of all these institutions and researchers. So the title is The Life Cycle of Volcanic Ash, Deciphering Deposits and Field Observations. So, so the outline of the presentation, I will start with the stages of the life cycle of ash and why are important. Then I will focus on aeolian remobilization, that is my focus of research. I will tell you a little bit of aeolian theory, the implications of eruptive styles, and what the field work and deposits can tell us. And I will do that through two case studies, Cordón eruption in Chile, Argentina, and the Vulcanian cycle of Sabancaya in Peru. And I will finish with the perspectives of this research. So the main goal of this presentation is that from now on, you will think twice before discarding a reworked deposit.
Lucia, we can't see your slides. Could you just share your screen, please?
Why you didn't tell me before? Where are you? I lose you. Now it's good. That's weird.
Okay.
Just a sec. Because I cannot open it again in my screen. Now?
Yes.
Okay,
yes,
I don't know why it get lost. Okay. But did you see the outline? No? Okay. So this is the outline, and then I pass here. So the first time that Manuel asked me to do the presentation, he told me about these volcanogenic sediments, and he told me to focus on something between genesis, transport, deposition, and diagenesis. So it's everything of the life cycle of volcanic ash. So then I thought in this scheme here, that I found very, very useful. It's from McAfee et al. It's a book on volcanic textures. And it goes from the genesis, volcanic eruption. So you have effusive and explosive activity. So then you have all the deposits related to, so lava flows, pyroclastic flows, PVCs, and fallout deposits. Then you can have these resedimentation processes. So here is written like resedimented syneruptive volcaniclastic deposits. And then you go through weathering, erosion, and the post-eruptive erosion, volcanogenic sedimentary deposits. So we can say, or we can summarize in pyroclast, autoclast, and here the epiclast. So actually, the difference here is that you have the primary class here, where it's related to the release of volatiles. And of course, if you have pyroclast, it's because you have a brittle fragmentation of magma. So these clasts are hot. They have high energy. And for epiclast, which is in the other corner, you have the non-volcanic processes, you have nodulenal mainly, and it's a result of weathering. So it means that you have physical chemical alteration. But in the middle of that, you have something that is still not really named, and is not related with volcanic processes, but involves quite a lot of juvenile and non-juvenile fragments called particles. And the most important to me is that it's no consolidated pyroclast of deposit. So then we go fastly to the life cycle of volcanic ash. So we have, as I said, the magma fragmentation. You can have either steady or unsteady styles, and this is very important because you have in the steady fragmentation, you have like an instantaneous release of large volumes of tephra. This is generally intermediate or silicic compositions, but it can be also basaltic. And the most important thing is that you have large volumes of fine ash. With the unsteady fragmentation, we are talking about this pulsatory activity that is mainly related to Vulcanian, violent Strombolian or Hawaiian. And this is mainly long-lasting cycles or sporadic explosions, small explosions, generally intermediate to basaltic, and the fine ash depends on this fragmentation efficiency. This is important because, of course, the number of particles that will be remobilized depends on their active style. And it has this implication on temporal and spatial scales of transport and deposition processes and the subsequent erosion. So then you have the volcanic plume, you have an eruption, explosive. So then you have this tephra dispersal, which will fall out by gravity. So then you have tephra fallout. And if you have dense columns, you can have these pyroclastic density currents. So in the end, you will have a deposit of tephra fallout and pyroclastic density current, mainly. But then these particles that fall can be remobilized, either by wind, either by water that we all know is the lahar, or here I just call it wind remobilization of ash. So all these particles that are subject to the wind will be entrained by the wind to the atmosphere again. So then after a long time later, you will have compaction of these deposits, lithification, and the weathering of those deposits going to epiclastic. So here we summarize again, we have pyroclast and epiclast, and something in the middle, which is these particles that are prone to be remobilized, that people normally call it reworking. I don't like that term because it's really vague and everything could be reworked. So I stuck from now to this term of McAfee of resedimented. I prefer remobilized resedimented by wind or water. In our case, I'm focusing aeolian remobilization of volcanic ash. So then a bit of aeolian theory, just to understand a little bit what happened with these particles. So you have mainly three transport mechanisms. And this is really related to the size of the particles. Because of course, you can imagine that the particles are on the ground. And once you have a certain velocity of the wind, those particles will be entrained. But the way of being entrained depends on the density, so the size of the particles. So it's generally accepted that particles larger than 500 microns, they will be like rather than entrained, are rolling, no? They suffer a process of reptation or creeping. But in this range, 70 microns to 500 microns, more or less, you have the saltation process. And this is the easiest process for the particles to be remobilized by wind. So the particles mainly start a jumping process, and this saltation can, depending on the size, can go or either long-term suspensions and that goes up in the atmosphere, or short-term suspension that goes like 20, 70 microns And so it means that it goes in the boundary of close to the ground. So all these process is related to these competitive forces of aerodynamic forces that are mainly related to meteorological conditions, so the wind drag and the aerodynamic lift, and the resistive particle forces that is related to the gravity, as I said, the density and the cohesion of these particles. So this competition of forces is can be measured or can be quantified by what we call the threshold friction velocity. So the threshold friction velocity is the minimal velocity that you need to start the motion of those particles. And theoretically, from the mineral dust theory, we know that this follows a U shape, and you have the minimized particles here, which is actually between 63 to 100 microns. So that means that these range of sizes are the easiest to be remobilized. And the smallest here, actually the threshold friction velocity goes up because these fine particles are so cohesive that obviously it's more difficult to get entrained by the wind. And the larger particles here are so big that are also difficult to get entrained. So this is mainly the theory behind this particle transport. Okay, so why this is important? Because we are telling about this particle size, because of course, when we have primary deposits, so we are saying PDCs and tephra fallout to connect again to the life cycle of volcanic ash, you have particles of a range of sizes. That could be, everyone knows, is tephra, so it could be ash, fine ash, coarse ash, lapilli, and blocks. So actually, the range for aeolian processes is between 0, well, let's say less than 20 microns to 500 microns. And depending on what I have said before, you can have suspension, saltation, or a creep of particles. So this is the particle size, and this is related to the magma composition, because the volcanologists, we all know that rhyolitic eruptions tend to have much a higher efficiency of fragmentation. So then we have much more fine ash than basaltic magmas. And then, of course, the morphology of particles is very important, because we are talking about microscopic scale. So the particles will connect each other and will aggregate, and these make the cohesion higher. So what the deposits will reflect? First of all, the class forming processes, if they are pyroclastic, autoclastic, epiclastic, and now I'm calling remobilized. The deposit will also show the transport and deposition, and of course the re-transport and re-deposition processes, the temperature of deposition, and the alteration processes. And this is coming again to this eruptive, the relation with eruptive style that could be steady or unsteady eruptions. So then the features that we will look in the deposit and will serve us to reconstruct is the grain size distribution. Then you have the volume of the eruption and the plume height, which is very important actually, because it is what we actually use to reconstruct the magnitude and the intensity of the eruption, the duration, and we can infer from the different stratigraphy of these deposits the eruptive styles. So this is key for forecasting hazards and assess a risk, which actually, in my case, because I have also this research, focus of research, is very important to understand what is the impact of volcanic tephra deposits in the people and in the environment. So then I arrived here, so I will ask you, Rebecca, to launch the a poll. It's a questionnaire I just want to know what do the audience think about rework deposits. So I don't know if I have to stop sharing. Just
It should be on the screen. Can everyone see that?
yeah. So I will ask the audience to just don't think too much. Just choose.
I can't see it.
It's in the chat.
It seems it's not working. I have a problem.
If you go into the chat, you should be able to click and vote.
Because I guess we don't have communication with the audience now to know if this is working.
Yeah, I can't use it. I'm sorry. So there is an error.
Probably if you have some results in your poll, otherwise we just skip it.
So the poll results, as far as I can see, is 0 people have voted for always. 37% of people have voted for many times. 18% of people have voted for sometimes. 37% of people have voted for almost never. And 6% of people have voted for never. I've never been in the field.
6% have never been in the field.
That's just one respondent. So our biggest response is either people have many times discarded reworked deposits or almost never discarded reworked deposits. So a split audience.
Yeah. Maybe you can just keep those percentage in mind for the end of the presentation. Let's see. Okay, that's a shame that people have not been in the field. Okay, that was the break. So now we pass to these 2 case studies. So we have, as I said, the fragmentation of magma. We have a steady and unsteady fragmentation, and this is important because, as I said, I just to recall that it's important in the terms of volume of fine ash, or it's fine ash because we are if you remember, it's from 0 to 500 microns. So this is important to know which kind of particles we have after an eruption. So I have these 2 case studies. Is Cordon Cauy eruption 2011, 2012, and Sabancaya. So the main differences here are summarized. So Cordon Cauy was a subplinian eruption. It emits about 1 cubic kilometer of tephra. It was rhyolitic in composition, and there was quite a lot of fine ash. So the plumes were about 8 to 14 kilometers above sea level. And actually, the climatic phase was the first 24 hours. Then there were some few months of explosions afterwards, but the vast tephra volume was emitted in the first day. And then the climate is arid, dry steppe. Well, we are going from Andes to the Patagonian steppe. For Sabancaya is in Peru, and this is totally different. So it's a pulsatory activity of volcanic explosions. So we have more than 8 years of activity with plumes that are quite lower, 2 to 5 kilometers. And the volume emitted is really very low. It's andesitic in composition, and the environment is very arid and dry. So that produced for the Cordon Cauy 3 years of intense and frequent ash storms, and more than 8 years of mild, frequent storms and ash devils. We will see what it is. And for Sabancaya is syneruptive. During the same time of the activity, we have an intense activity of remobilization. So just for you to see what it means, this is Cordon Cauy eruption. So as I said, it was about 2 weeks, but actually the vast tephra was 24 hours, the first 24 hours, subplinian, and some intermittent explosions afterwards. And this is to you to see a little bit what suspension means in the atmosphere and for the people, the communities that live in these areas. This is about 300 kilometers far from the volcano. And you can see also the persistence of these events, and that continue in the time years after the eruption finished. Okay, so that's Cordon Cauly. So we go here. Just this is the 11th of June. The eruption was the 4th of June. So this is one of the smallest compared to the main explosion the first day. And then you can see, this is interesting because you can see already the deposit, which is very large. It covers the Patagonia here. And here you have this aeolian remobilization that is related, of course, to all this loose material that is here. You have okay, I go here. You have this profile. So the volcano is in the Andes, in the Cordillera, and then you have Villa Langostura, which is here, Bariloche, San Carlos de Bariloche, and Ingeniero Jacobazzi, that were the main communities that were affected because they were, of course, distributed in the main wind direction. And you see here that you already have a climate gradient going from the Andes to the steppe. So you already have here some pictures of how that looks like. And these are the pictures of the deposit. So here is primary deposit. And here in 2016, we have I have been there in the field to see these deposits. And 5 years later, what it was very interesting is that we could actually compare the field observations during the eruption, or some days after the eruption, and 5 years after. So what we have seen is that the primary deposits better preserved, of course, in the rainforest. And here, they are preserved in these small valleys. When you have like wetlands, you can have some preservation of deposits. Otherwise, the primary deposit is almost gone by the wind. So you have the remobilization here on mountains, mainly where there are mountains of high altitude and absence of vegetation. And here you have a remobilization that is strongly enhanced for all over the surface, and the primary deposit almost disappeared. So the next observations will be here in this area. This is the Patagonian steppe. And what we have distinguished is two kinds of deposits. One is no deposits associated with no erodible elements, that are vegetation and rocks. So normally, and this is very important, we have the deposits, the vegetation act like a windbreak. So that absorbs the momentum and reduce the wind speed, the velocity of the wind around the plant. So that makes the plants like traps. And depending on the species, depending on the quality of the plant, the age, you will have better traps or not that better. So generally, you have also these interpatch areas in between the vegetation cover that actually very, very typical of dry and aeolian conditions. Then you have the deposits that are associated with one of these sites of before windward the plant and leeward the plant, and the interpatch. So we have done a very, very detailed analysis of the grain size, and we for what we did that, because we wanted to compare the primary particles and the remobilized particles. And from that detailed analysis, we could somehow conclude or infer if these particles went in saltation or suspension, even though it was a deposit already and we haven't seen the phenomena itself. We also use the morphology of the particles to compare. I mean, the work basically was to compare primary particles and remobilized particles because we have the samples of the primary deposit. So then we arrived to this interpretation of the plant. So actually you have the wind direction once the particles start traveling and let's say that hit the plant. What happened here is better. You have a view of the ground. You have the wind, and the wind will the streamlines of the wind will diverge around the obstacles. In this case, are mainly plants or rocks, and become compressed. And then you have these stagnation zones before and after the plant, and generally before, after the plant, the deposits are larger. We have seen that very commonly in Patagonia. So then we have different kind of plants. As I said, it's a very dry area. So you can see, for example, this one haven't trapped anything of ash, but in other cases and more healthy plants can trap much more ash. And then those are deposits, as you see, this is the windward and this is the leeward of rocks. So then the other kind of deposit that we have seen is those related to the pre-existing dunes or other erodible bed forms. We call it like that because in Patagonia, we have this geomorphological unit. Is mainly like depression and lowlands that forming a kind of dunes. We can call it dunes, that they are not the same dunes that we are having in the desert or in the beach. But these bed forms promote like the trapping of ash mainly in the leeward side of these mounts. And we also have seen here, it's a kind of a mess because we have huge or massive coarse ash layers and fine ash lenses like these ones. So then we interpret this like a cross lamination that was related to the saltation creep processes of the dunes. So actually here is the explanation. Schematically, you have the particles that start salting here. So this is the detachment area and this is the position area. So the wind will follow the form and make the particles saltate until they arrive to the point of the streamlines again become compressed and become zero, let's say, and it creates a shadow zone behind this mount. So in the separation, here is the separation, and then the particles that have been saltated will fall, let's say, here and rolling here in the slope of the dune. So you have this recirculation of eddies, provoking also some granular segregation, and then is an interpretation of how we could have fine particles roll down here, and this is the fine lenses that we have found. So this is another picture of that. That, of course, is not our ash, it's not cordon cave ash. It was another dune in the same area made of all these sediments that obviously are volcaniclastic because all the area is volcanic. Okay, so then we arrive to Sabancaya, and you will see the difference of explosions, the size of explosions, and the activity is completely different. So you have 6 to 42 explosions per day, very small. So the dispersal is very reduced. Here you have simultaneous, this is remobilization, and this is the primary cloud. And this is in high speed one day in Sabancaya. So actually you can see how dynamic is the process in this altiplano. Okay, so this is Abancaya. And as I said, you have this persistent but intermittent simultaneous activity, and that makes it really difficult to interpret any deposit and the phenomena. So then the conditions are totally favorable for aeolian remobilization. It's a very, very dry area. The precipitation is less than 100 millimeters per year. You have strong winds, scarce vegetation cover. You have these small things here that are not really trapping all the ash. And then you have the snow cover in winter. So it's very mixed, the remobilization in this area. So those are some pictures. You can see, I mean, what it looks like in the different plants. Here is a deposit. And here some ripples formation. Sometimes you are totally encouraged because it's very difficult to interpret what was primary, what is secondary, and what is the relationship between the two. And sometimes you just get fun and destroy the work of the wind. Okay, so this is the interpretation. So to me, it was a really hard work because as a volcanologist, you always want to study the deposits that are not reworked, that are primary. And here was almost impossible because all the sites that we have studied have somehow these structures, so cross lamination, some structures of aeolian. We try to sample the upper layer to see if there were some differences in grain size and so on. And the conclusion is that we couldn't. And we couldn't because we have seen how dynamic is. You have an explosion, then you remobilize, you have an explosion, then you remobilize, and so on. So all these deposits that have been interpret these two layers, because there were at least two layers that we could correlate, the A and B. So we associate those to the 2016, 2018 that we were in the field with the actual cycle. And here, the layer C, we correlated with, we believe, is the 1998 cycle. So it's very difficult because there is also the stratigraphy of the cycle, the precedent cycle, and it's very difficult to distinguish what is what. Okay, so then because of this complexity, what we have tried is to build a field strategy. So we build on the traditional deposit characterization, but then in the sampling, we have the primary and remobilized particles in situ. So we use this adhesive paper to collect vertical falling particles and horizontal particles. You cannot believe, but this is me collecting something horizontal. So it was the ash wheel coming to me and collecting the particles that were coming. And then we have these vertical collectors, which is actually the common use now in South America, at least, to collect the primary tephra and the PM10 measurements we have. Then we have some video analysis, high definition and high speed videos to actually look at the particles and see the phenomena and how the particles, the transport mechanism. And then we have, but we call it saltation experiments, and it's something, the scheme is here. So we try, actually I have a picture, yeah. We try to do a kind of experiments in the field, so collecting the particles that were saltating in the adhesive paper and measuring the wind conditions at that moment. So it's something that was, as you can see, very easy to do in the field. Then the high-speed video analysis was very useful, actually, because it allowed us to see and represent the saltation and creep processes of these particles. and also to characterize or to observe in the field this splash effect that is actually in the Eolian theory. It says that the saltating particles, which is the easiest transport mechanism, will trigger the suspension of the finer particles. And we have seen that with these videos is true. I mean, you have the saltating particles that are easy to go jumping and creating like a splash of the finer particles. So then, to conclude, with all these strategies that we have built in the field, we calculate the volumes, we characterize and classify the lithometeors, so the phenomena are called lithometeors, and now it's more standardized with the Aeolian theory as well. We correlate the Aeolian transport mechanism, and we characterize the grain size and the morphology. And this was very important compared to cordon cauye, and is that here, being an overlapping process, you cannot really distinguish the particles as we had done in cordon cauye. And this is to say that the eruptive style and obviously the syneruptive and post-eruptive processes need to be adapted to the activity, to the volcanic activity and the subsequent erosion. So this, to conclude, I mean, you have the two case studies, cordon cauye and Sabancaya, and the differences are that in this case we have a clear distinction between primary and remobilization. In the case of Sabancaya, it was really a confusing overlapping of the layers. I mean, in the end, it's a massive layer of primary and secondary phenomena. Here you have a clear distribution of the deposits. The primary deposit almost is inexistent in the most distal areas. Here is different because you have a kind of redistribution of all together, primary and secondary. And as I said before, for cordon cauye, the grain size and the morphology were key to interpret the mechanism of transport instead of Sabancaya, that was not really possible. And that's why we use this multifaceted field strategy, combining real-time measurement, sampling, and image analysis. And of course, something that is very important if we really want to characterize primary and secondary phenomena is that we have a rapid characterization of the primary deposit. Otherwise, it's really difficult to understand what happened after. Just to conclude, well, the characterizing Aeolian remobilization is key to construct the future eruptions and better estimate the volumes, because in the end is what could be one of the most important consequences of this Aeolian phenomena. Something that is very important is the tephra deposit preservation. So that depends on vegetation, mainly humidity conditions and topography. So it's true that rich vegetated and wet landscapes will reduce the Aeolian remobilization effects. And this is important for the communities that live there. For example, in Patagonia, that you could have a action on those on the vegetation cover of the area that are at least habitated. And of course, thinking in the past deposits, we should consider Aeolian remobilization to interpret these past eruptions. The perspectives for the future, we are working in many different areas because before it was really let's say neglected. The Aeolian remobilization of ash now is much more important. So we are working a lot in how to distinguish primary and remobilized deposits. But I have to say, me personally, I have worked with primary tephra fallout, but not PDCs, which will really complicate much more the picture. We are working on all these strategies to collect data in real time or in long term. Then we want to collect mass flux or mass transport the surface conditions and the meteorological parameters in real time are very important to interpret and to understand these processes. Then with the laboratory methods, I have to say that you create a lot of data, because then you duplicate the samples, because then you need primary and secondary, and it's really a lot of work. So it's something that we have to work better in how to create a strategy, a methodology for the lab to analyze mainly the grain size, morphology, and density, which is actually something very important, because in the Eolian theory, in the mineral dust, which is sand, they don't account for the vesicularity of these particles. But for us, for ash, it really changed everything. So this is something that is still a work in process. Then experiments, this is something very interesting, is that, as I said, mineral dust have worked already since the early 90s, 1940 or something like that. They start already measuring the threshold velocities to get the sand getting trained by the wind. But in ash, we just start, so this is very pioneering works that have been in the wind tunnel. This is a wind tunnel in the University of Aarhus, and this is to in laboratory conditions how we can measure the threshold friction velocity that starts the motion of ash and not the sand. Then Del Velo have done also these experiments in the field in situ. And then we have also, we came back to the Aarhus laboratory to measuring different ashes. So you will see some particles here, and a different strategy to visualize the particles in the wind tunnel and measure this threshold friction velocity, which is actually key for the models. The remote sensing is very, very important, because for the small events cannot be visualized with remote sensing, but the big ones, yes. And this is something very important, because sometimes in the Andes, happen a lot in Alaska as well, in US, is that the clouds of remobilization could be so big that could be interpreted as a primary eruption, as an eruption, and that are a false alarm. And this is something that the VACs are working on, because apparently it's very frequent. So here, so that is for distinguishing primary and secondary clouds. And then here is another example of how to characterize the big events. And this was related to Cordon Cauye. It was a big event 4 months after the climatic phase. And they have to close the airport of Buenos Aires. So it was really a big event. So they could model this event using full 3D. And in the end, this is actually the let's say, the importance of all this research is to better forecast the events, because as in the same way of primary eruptions, the idea is to forecast the events and the dispersal of these particles when they get suspended, and of course all the impact that could generate, not only in the air traffic, but in the communities that are exposed to this remobilization of particles. So for the moment, these models are based on the mineral dust and the tephra dispersal model of Fall 3D. But the idea is to actually better constrain the parameters for volcanic ash. Okay, so we finish. I hope I cover all as I said, and I hope that you will think twice now before discarding a reward deposit, and change a little bit the percentage of the fault that we have at the beginning, even though it's actually very difficult to work in this area. So for sure, you need good glasses.
Okay, thank you, Lucia. It was very nice, your presentation. I don't know if there is questions in the chat. If someone have any
If people
question.
could pop the questions in the Q&A, that would be helpful. I just saw someone's hand go up, so I can try and unmute you. But I think you might have just put your hand down because it's disappeared off my screen. But I can try and unmute people if they want to ask in person. Otherwise, pop the question in the chat. I guess to get us started with the question, Lucia, I was really interested in a really lovely talk. Thank you so much. How much do you think not paying adequate attention to ash remobilization is causing those who are trying to understand eruption histories to perhaps overestimate the number of eruptions, or do you think it's an underestimation? And I guess also the same question in terms of eruption volumes.
Yeah, I think it really depends on the, as I said, in the eruptive style that happened in that past eruption and the landscape that was at the time. If you think in an island, for example, and the volumes are already somehow, I mean, the estimation of volumes is very difficult because you lose the sediments, so you lose the deposit. Then in the case of Andes, for example, that you have these old deposits of large eruptions, for sure there was it's difficult to say if it's an overestimation or underestimation of the deposit because depends where the site was mapped. As I said, in my experience in the Patagonia is that you have areas where there were huge amounts of tephra, like redistributed and redeposited. And if you think in all deposits, it's difficult to see how much those sites that were studied were affected by the mobilization. And sometimes with the compaction, it's not that easy to see. I mean, it's not like a perfect dune. It's not this aeolian process where you have the cross lamination and cross bedding, and you can clearly identify the differences between the primary and secondaries. That means that you have doubling, for example, a volume, which is actually not the case. It wasn't the case. And the other thing that to me is very, very tricky is that you lose the fine material, because the finest material, it really goes long-term resuspension. It means that goes in the atmosphere and is not there anymore. It's not there. And this from the point of view of the magnitude of the eruption is important, because of course you need you study the grain size distribution of these primary deposits, but actually the fine ash has gone.
Thank you. If anyone wants to add any more questions to the Q&A or into the chat, we can monitor those. I had another one, Lucia. Sorry. Whilst everyone's being a bit shy about questions, I really liked your the diagram that you had comparing primary ash to remobilized ash, and I don't know if that is something that you've already published or as part of that work that you're currently doing now. But it strikes me that the remobilized ash has loads of similarities with dilute pyroclastic density currents, and that many people, if they saw cross-bedded ash deposits in the field, would interpret that as a dilute PDC. And I was wondering if there's any key features that you'd be able to maybe have a third column on that to try and pull apart that distinction.
Yeah.
If you had any thoughts on that.
Yeah, actually, that's the idea. I have not worked with PDCs previously to this work. So, but this is the idea, to have someone like more with more experience in PDCs, and try to get on that, because yeah, exactly, because there is some differences, because you can have for the PDCs, not well, the diluted, you have much more fine ash. As far as I understand, I'm not an expert on PDCs, but you have much more fine ash than what you will have here, because it's true that this range, limited range between, let's say, 50 microns to 100 microns, is really limited to the Aeolian range. Whilst the PDC could be different, right? It could be much more finer. And another point is that you, in a more regional view, you will have one source for the PDC. This is what you expect. I mean, you have the collapse of the cloud of the column, and then you will have one source of the PDC. Here, no, because you will have several sources. I mean, you have this is one of the main problems actually for the models. You have a surface of emission sources, and these will be different of PDCs. And the other thing is that it could be, I mean, obviously it depends, but how where you have the PDC. But of course, the Aeolian will follow the main wind pattern, the surface pattern, which is not the main, is not the atmospheric wind. And this is something important also to consider. It's not the atmospheric for the cloud, but it's the surface pattern of the wind. Normally you have a prevailing wind. With the PDC, no, because it's not depending on that. But it's still really something to explore.
Great, thanks very much. Okay, Andrea?
Yep. So quick question, sorry, just because I generally work on very old volcanoes. Okay, so interpretation on the stratigraphic sequences of all volcanoes is really complicated. But anyway, do you think that those kind of processes could also be beyond the Aeolian one, like controlled by geochemistry of magmas and so of the eruptions?
Well, if you say all deposits, but consolidated, not consolidated.
Well, this again is just because very consolidated. I mean, like Oligocene deposits and so on. The interpretation of those kind of processes are really difficult. Sometimes you don't have the source. So just to have an idea on to have an idea about chemistry, geochemistry, and then processes. So
I will say that, and this was part of the very beginning of the presentation, when I start thinking in volcanogenics terms. Obviously, epiclastic processes are totally different. And you not totally different. Of course, there is the agent of erosion, but then you have these chemical, physical properties that will change with the time. But the Aeolian, I mean, the very, because then in time is very close to the eruption somehow, even though we have remobilization millennia after the eruption, but have need consolidated. That's the important thing.
It's okay.
So, but in that sense, the chemical, because the alteration, but what I wanted to say is that in that sense, I don't see that the timing of, the time scales of a remobilization could affect that much the composition or be like a driver of alteration. I don't see it. No, I don't. In any case, from my experience that I have seen in Patagonia, or which are very dynamic is very strong weathering process, I haven't seen it, not in that time scale.
Okay.
So chemistry will not be a good indicator, I would say.
Okay, thank you. Oh, there is a question again by Leandro.
Okay, I'm just trying to allow your mic. Okay, if you unmute, Leandro, you should be able to talk. You need to unmute your mic first. There we go.
Okay.
Thanks for the presentation. Very nice. I have a question related to you refer always to surface or subaerial examples. What about ponding waters or lake? If you did a comparison between the remobilization and primary deposits. And the other question is a similar question related of Andrea, related what do you think about the deposits that we found in the ancient sequences and we describe like primary deposit in these areas? Because your presentation stress about the huge remobilization about this deposit. This is the true question that I have. Thank you.
But sorry, the second question, could you repeat me the second question again?
Yes. The second question is, what do you think about when the volcanology describe primary deposits in distal areas of volcanoes? Because you refer a different process of remobilization and something that the deposit haven't got the texture related to primary deposit in proximal areas. But when we found, for example, very fine ash layer deposits in this area of thin deposit, or maybe we can refer to primary deposit of eruption. Maybe the record is, but what do you think about in the mid-term or in ancient deposit, the representation of primary ash deposits?
Okay, so yeah, we'll start with this one first. That was somehow related to the previous questions as well, for the volume estimation and the distinction and the stratigraphy record. To be honest, I'm really concerned about past eruptions and the interpretation of those and the volume estimations, because if I take the example of Cordon-Caille, it wasn't super big, but still it was BI 4.5. It was 1 cubic kilometer of tephra, and the deposit like 300 kilometers far were like at the very beginning it was like 7-10 centimeters of fine ash. And 5 years after, when I went, there were some traces of this, but 10 years after I went, no, 9 years after I went again, and it was almost nothing. It was almost nothing. We couldn't actually find it to do these experiments of the wind tunnel. So we are talking about 200, 300 kilometers distal. So it's incredible, actually, because it means that for all the eruptions, we have, let's say, over or underestimated. We have these deposits, and you find something, and you map, and you try to draw this isopac map, and you try to constrain the volume. But you always need the last isopac to finish your deposit, to delimit the area and reconstruct this volume. So I wonder if how much we will, underestimate in this case this primary deposit that doesn't exist anymore. So that, again, I mean, I don't have the answer. We are like discussing quite a lot how to first how to quantify volumes, which are very random, right? I mean, they follow up wind pattern, but they are very random. I mean, when you are in the field, sorry for the people that haven't never been in the field, but when you are there, it's really random. You don't know how to, I remember someone tried to, from the Roche Agriculture Sciences, tried to measure the geometry close to each, in the windward and the leeward of the plant. But it didn't, as far as I know, she didn't arrive to any answer because it's really difficult. So I don't have the answer, actually. I don't have it yet. And for the other part of the question, the first question, I have, well, even I think the few days after the next week or something, it will, we will have a paper of Hudson. And this is with a collaboration with a group of the St. Andrews University, and they are geographers, and they have another view, and they have worked quite a lot with deposits of limnogeology and deposits in lakes. And there is a comparison with the reworking processes aeolian in the ground, on the ground close to lakes, and the deposits that they found in the lake. Which, and then it was quite difficult because there were the discussion of if these particles of these deposits that they have in the lake have been already remobilized by wind, and these particles arrive to the lake. And then you have also these turbiditic processes in the lake. So that makes, they have the cores, and we have, they particularly have been super deep on this analysis, and this is a paper that will come very, very soon in Frontiers of Hudson. But then you add to the complexity because you have wind and water remobilization.
Thank you.
Okay, so I think that we reached the hour. Very good. Now, just last question.
I'm afraid that I think people are leaving, so I think we should call the webinar to a close.
Okay, so let's close the webinar now. I'm sorry for if there are other questions. Please reach Lucia by mail. Thanks a lot, Lucia, for your great presentation. I think that was a very, very interesting presentation for many different aspects on many different topics that can be developed. Obviously, thank you, Manuel, because today Manuel was our leader of the webinar. We are inviting you to the next webinar, which will be held at the end of November, probably. We will have a New Zealand guest, so remember that the time will not the European time, but will be the New Zealand time zone 1. If you lost the other webinars, just go to our YouTube channel. We have a YouTube channel, and follow us on our social media to have news about new webinars, schools, and so on. So keep in touch, and see you next month.
Thank you very much. Thank you.
Bye-bye.
Bye-bye.